Hello, good evening, everyone. So today we are going to discuss uh, we'll discuss the problems based on the lectures taken in the week 12 in the NPTEL portal on the course of Principles of Signals and Systems. So today is the last week of this tutorial session. So we'll discuss some of the questions based on whatever is taught in the week 12. So mostly we'll discuss about filters like IIR, FIR, finite impulse response filter, and infinite impulse response filter. And we will see different methods how to block diagram, how to make the finite and infinite response filter. So before that, we will take one easy questions. So first we'll take one questions that is based on the graphical approach, convolution based on the graphical approach. So the question is perform linear convolution and circular convolution using graphical approach on the signals x1n is equal to 2 1 2 comma 1 and x2n that is equal to 1 2 3 comma 4. So we will find using the first we'll find the linear convolution. So x3n, so here x3n will be the convolution of x1n and x2n. So in this question, we have to perform the linear convolution. So using the graphical method. So first what we will do, we'll write x1n and x2n. So x1n is here 2, 1, 2 and 1. X2n we will write here that is 1, 2, 3 and 4. So here when you do 2 into 1, you will get 2. Here 2 into 2 will be 4 and 1 into 1 will be 1. So similarly, we have to complete this table. 2 into 3 is 6, 8. Here it will be 1 into, that is 1, 2, 3, 4. Here is again 2, 2, 4, 6, 8. And here it will be 1, 2, 3, 4. So just draw the graphical table like this. Now you add it. So x3n that is equal to 2. The first element is here 2. Second is sum of these two. So 1 plus 4 will be 5. Third is 6 plus 2 plus 2, 10, comma, 11 plus 4, 15, 1, 16, 12, 11, and 4. Now you can see the length of the x3n is 1, 2, 3, 4, 5, 6, 7. That is length of x1n plus x2n minus 1. 4 plus 4 minus 1, that is 7. So in this way, we can solve these kind of questions. Also, a few questions we will see based on the properties. Well, if you remember some properties, it will be easy to solve any question for us. So the next question is the DFT of a real value signal is given as xk, that is equal to 10, 2 plus 3j, comma a, comma 3 minus 2j, comma minus 5, comma b, comma 2 plus 4j, comma c. Evaluate the values of a, comma b, and c. So in this question, we have to find the value of a, b, c. How we can find? We need not solve these things. We know that using conjugate property of real valued signal, xk is equal to x conjugate of n minus k. So we will use that property to solve this question using conjugate property of a real value signal. So in this, xk is equal to x conjugate of n minus k. So now a is equal to x2. A is the value of x2 here. So that is equal to x conjugate of n is here 1, 2, 3, 4, 5, 6, 7, 8. N is 8. Let's suppose this is 0th index, this is 7th index. So our n is 8 and a is at the second index. So that is 8 minus 2. So what is our 6th index? That is this. So that is x conjugate of 6th. So that will be 2 minus 4j. Okay. And b is equal to, here you can see this is fifth one, x of 5. So that is equal to x conjugate of n minus k. So here n is 8 and k is 5. 8 minus 5, that is equal to x conjugate of 3. So that will be 3 plus 2j. Next is c. C is x of 7. So this is equal to x conjugate of 8 minus 7. So this is equal to x conjugate of 1. So what is the value at 1th index? It is 2 plus 3j and the conjugate will be 2 minus 3j. Okay. So in this way, these questions can be solved. Now we will see some of the digital filters and the basics of that. So in filters, we know that filters, the purpose of the filter is to accept certain types of signals and reject others. So this is just a definition. So purpose of the filters is to accept certain type of signals and reject others. So filter can be characterized by its frequency response, that is low pass filter, high pass filter, band stop and band pass filter. Okay. So we will see different kind of filter. Filters can be characterized by its frequency response, that is low pass filter, high pass filter, band stop and band pass filter. So we will see the frequency response of these filters. The first one is, let's suppose, take the low pass filter. So in low pass filter, what happens? It allows the signal, the lower frequency part of the signals to uh, go out and filters out the higher frequency component of the signal. So this is the transition band. This is WS. After WS, it does not allow any signal to pass. And this is WP, that is the pass band. Okay. And after WS, what is that? That is the stop band. Means it won't allow those signal to pass. Okay. So this is just a low pass filter. Now this will be the cutoff frequency, that is FC. Okay. Now next is the high pass. So in this, higher frequency component of a signal is allowed to pass through the filter. So somewhere here this will be FC, that is the cutoff frequency, and this is the frequency response. Now the next one is band stop filter. So in this, some part of the signal is stopped, and the remaining part is allowed to go through the filter. So this is our pass band. Then again, this is a stop band. So this area is known as the stop band, and this area is known as the pass band. and it have two cutoff frequency. One is lower cutoff frequency, that is FCL. One is higher cutoff frequency, that is FCH. Okay, so this is known as band stop filter. The fourth one, that is band pass filter. So in this, the certain band of a signal is allowed to pass through the filter. So this is the pass band, and the remaining part of the signal is filtered out using this filter. That is a stop band, and this is also a stop band. And this is our lower cutoff frequency, and this is our higher cutoff frequency. And you know, the cutoff frequency is decided where the 70% of the signal is passed or not. That is 1 by root 2, that is 0.707. So this was all about the high pass, low pass, band stop, and band pass filter. Next, we will see Butterworth filter. We will directly write the formula. We will not go into the deep. So a Butterworth filters of order k is defined as. We will see the formula of that. That is magnitude of h omega. That is mod of h j omega is equal to 1 by 1 plus omega by omega c. Omega c is the cutoff frequency to the power of 2k. Here k is equal to 1 comma 2 comma 3, and whatever is the value of k, that is the order of this Butterworth filter. So we'll solve some question. One question. Determine the transfer function of Butterworth filter of the low pass type of order k is equal to 3. Assume that the 3 dB cutoff frequency omega c is equal to 1. So in this question, we have to determine the transfer function of Butterworth filter of the low pass type of order k is equal to 3. And in such a way, and also it is given that the 3 dB cutoff frequency omega c is equal to 1. So for filter order k is equal to 3, 2k will be 6 poles. Like in the denominator, it is 2k, so it will have 6 poles of hs and h minus s are located on a circle of unit radius. So we will take the left half plane poles of hs, and we will define that, and accordingly we will create a characteristic equation, and we will find the transfer function. So first write this point. For filter order k is equal to 3, then 2k is equal to 6. Hence, it have six poles that are located on the unit circle. We'll draw the diagram also. Unit circle means circle with radius 1 with angular separation of 60 degree because it has 6 poles. So we will draw that circle. So this is 60 degree, again 60 degree. This is our omega c. This is minus omega c. This is the two six poles given here. This is minus, sorry, plus j omega c and this is minus j omega c. So here this part is minus half and this is root 3 by 2. Then our pole will be s is equal to minus half plus j into root 3 by 2. One pole is s is equal to minus 1 because omega c is equal to 1. And the third one is minus half minus of j into root 3 by 2. So these are the left half plane poles to HS. HS or HJ or what. Then our HS will be 1 by S of plus 1, S of plus half minus root 3 by 2j, S of plus half plus j into root 3 by 2. So after that it will become 1 by S plus 1. This term will be S plus, when you multiply it you will get S plus half square minus root 3 by 2j square. So after simplification, we will get 1 by s plus 1 s squared plus 1 by 4 plus s minus that will be 3 by 4 and j squared is minus 1. So minus 3, that will be plus 3 by 4. So when you substitute when you simplify all the values, you will get 1 by s plus 1 into s squared plus s, and this 3 by 4 plus 1 by 4 will be 4 by 4, that is 1. So this is the transfer function of the given Butterworth filter. In this way we can find. So now we will see like systems for filtering the continuous time signal. Built around the digital filter. How digital filter is used to filter the continuous time signal. This video is recorded also, so whoever missed this lecture can see it later on the YouTube. This video will be uploaded there and the link will be provided in the NPTEL course. So First input signal is given to analog to digital converter. Okay. So this is our input signal xt is given to analog to digital converter. So this xt is an analog signal. After given to analog to digital converter, it is converted into xn, that is the digital signal. Okay. Now we can apply digital filter on this digital signal. Once the digital filter is applied, we will get y of n. Now this, what we will do, we will again convert it to digital to analog converter so that the reconstruction of signal can be happen. Digital to analog converter. And here we will do some reconstruction so that the signal contains all the information, the no information lost. We will try like that. And here we will get the output signal yt. In this way, like input signal, continuous time signal is used. This filter is using a digital filter. The reconstruction can be done so that there is no loss of information. So now we will see structures of IIR and FIR. So there are different signals. So FIR signal, that is the finite duration impulse response, digital filter, and IIR, that is the infinite duration impulse response. So first we will see basic structures for IIR systems. We will solve some question on this. Let's suppose a signal Yn, that is given as k is equal to 1, capital N, k k, y of n minus k, plus k is equal to 0 to capital M, pk, x of n minus k. Then here our hz will be yz by xz, that is given as summation of bk to the power of minus k. Here k is equal to from 0 to m, and that will be m0. And here k will go from 1 to n, and it will be ak z to the power of minus k. So this is the transfer function, and we will first see how to represent as a direct form one. So we'll go into the new page. So this form is directly, like this structure is determined directly either from the equation. So here first is x1z that contains all the zero. After that x2z that contains all the poles, and finally we get xyz on yn. Okay. So this S2Z is for representing the poles. Here in between, let's suppose that is WZ or WN. This H1Z is for zeros, and here it will be XZ or x of n. So Wn that is equal to summation of Vk n minus k, and k is equal to 0 to n. And our yn that is equal to summation of ek y of n minus k plus w of n, and k is equal to 1 to n. So now when we take z transform, we will get wz that is equal to xz summation of ek z to the power of minus k, and k will be 0 to n. Okay, so this we have taken the z transform of wn, and we will take z transform of yn. We will get y of z that is equal to y of z summation of k is equal to 1 to n ak z to the power of minus k plus w of z. That also is equal to w of z divided by 1 minus summation of ak z to the power of minus k, and k will go from 1 to capital N. So now we will see how is direct form 1 is like can be like digital system structure of direct form 1. So here this is our, let's suppose, xn. The first coefficient to xn is b naught, and after that the z inverse delay element is given. So it will be x of n minus 1, and again one delay element is given, that is z inverse. So this point will be x of n minus 1. This point will be x of n minus 2. Like that, so on we can go here. Let's suppose this is x of n minus n plus 1, and we give one the last delay element, then it will be x of n minus n. Okay. So here we will get b1. The next coefficient is b1 here, and this coefficient will be b2, and the last coefficient will be b of n, and here the coefficient will be b of capital N minus 1. So we get this as a w of n. Now we will take like all these were for the zeros part. Now we will take for the pole part. So here we will get y of n. After adding a delay element, we will get z inverse. We will add one more delay element, that is z inverse. So we'll add the delay element at the end and we'll multiply with all the coefficients. So here it will be an. Here the coefficient will be an minus 1. After that, here the second coefficient, here it will be the first coefficient, that is a1. Here the second coefficient a2. And so on, all the coefficients are added. After adding all the coefficients, so this term will be y of n minus 1, this will be y of n minus 2, and this will be y of n minus n plus 1, and this will be y of n minus n. So this is the direct form realization of the nth order difference. So this is direct form 1 realization of an nth order difference equation. So now we will take one example and we will try to solve that. Okay. Develop a direct form 1 realization of the difference equation yn is equal to b naught xn plus b1 x of n minus 1 plus b2 x of n minus 2 plus b3 x of n minus 3 minus a1 y of n minus 1 minus a2 y of n minus 2 minus a3 y of n minus 3. So this is the difference equation given. So first what we will do, we will find the transfer function, that is hz, that is equal to yz by xz. And after that we will develop a direct form 1 structure. So first, taking z transform on both the sides, we get transfer function. The transfer function is hz, that is equal to yz divided by x of z. So here we will first take all the coefficient. Here you can do like this. Yz is equal to, let's take first the both the sides, we will take the z transform. So after that we will get y of z is equal to b naught x of z plus b1 z inverse x of z plus b2 z to the power of minus 2 x of z plus b3 z to the power of minus 3 x of z minus a1 z inverse yz minus a2 z to the power of minus 2 y of z minus a3 z to the power of minus 3 y of z. So now you take common. So y of z term you take common. So it will be 1 plus a1 plus a2. Sorry, y plus a1 z inverse is also there, plus a2 z to the power of minus 2 plus a3 z to the power of minus 3. Take all the terms of y of z in the left hand side. Then you will get the equation in this form. And here x of z b naught plus b1 z inverse plus b2 z to the power of minus 2 plus b3 z to the power of minus 3. So the transfer function hz, that is equal to yz by x of z, that is equal to b naught plus b1 z inverse plus b2 z to the power of minus 2 plus b3 z to the power of minus 3 divided by 1 plus a1 z inverse plus a2 z to the power of minus 2 plus a3 z to the power of minus 3. So first we got the transfer functions. Now we will draw the uh, structure. So first we will give x of n. Now we will add a delay element, and we need three delay elements in this case. So all we have added the three delay elements in the x. Now the coefficient you see, like in the zeros, the first coefficient is b naught. So multiply with b naught and you sum it here. The second one coefficient is b1 and again you sum here. The third coefficient is b2, again you sum it here. And the third coefficient is b3. Now in the pole side also there is three poles, so we will add three delay element because it is up to z to the power of minus 3. And the first coefficient is b naught, and it will be minus a1, minus a2 and minus a3. And here we will get our y of n. So this is the way to represent in the direct form. One, in direct form two, what we do, like the same thing, we can reduce the number of storage element, that is the delay element, that is z inverse, and we can write the direct form two structure. So we can see first how to write the direct form two structure, and then we can solve one question, or better we let's solve one question, and after that we can draw it. In direct form one, first first the poles are realized, after that the zeros are realized. So let's draw one direct form two structure, then we will get it more easily. So in direct form two, h of z that is given as h1z into h2 of z. Here h1 of z is equal to 1 by 1 minus summation of k is equal to 1 to n ak z to the power of minus k, and h2 of z that is equal to summation of bk z to the power of minus k, and k is equal to 0 to m. So here in direct form 2, first the poles are realized, after that zeros are realized. This is our W of z or W of n, or you take x of n or y of n. So here W of n that is equal to summation of k is equal to 1 to n ak W of n minus k plus xn, and y of n that is equal to summation of k is equal to 0 to m bk W of n minus k, and W of z that is equal to x of z divided by 1 minus summation of k is equal to 1 to m ak z to the power of minus k, and our y of z that is equal to W of z summation of bk z to the power of minus k, and k is equal to 0 to m. So the direct form 2 structure is denoted in this way. So in this, the first pole is realized, after that zeros are realized. Now you can see we can reduce the number of storage element here, and number of storage element is maximum of m or n. Now you can see that this portion can be combined together. So this is the direct form 2 structure. So in this we can draw simply. We'll make it a small. So after combining this structure, we can simply write it as x of n we can easily remove the number of delay element, that is also known as the storage element. So in this way, the number of storage element can be removed, and this is the direct form to structure. Okay. So now we'll solve questions based on this, and after that we'll see one example on the cascade form also. Determine the direct forms 1 and 2 realizations for a third order IIR transfer function given as h of z, that is equal to 0.28 z squared plus 0.319 z plus 0.04 divided by 0.5 z cube plus 0.3 z squared plus 0.17 z minus 0.2. So in this question, so first what we'll do, we'll multiply the transfer function numerator and denominator by 2z to the power of minus q. Numerator and denominator by 2z to the power of minus cube. So after that we will get h of z as in the form of what we have studied before, divided by 1 plus 0.6 z inverse plus 0.34 z minus 2 minus 0.4 z of minus q. So now we will see the direct form 1 structure. So in this x of n is given, we'll add three delay elements. The coefficient first is 0.56, second is 0.638, and the third one is 0.0, sorry, there is one zero less here, 0.08. There is no need of plus here because you can directly give the, and The first one is minus 0.6 from here. The second one is minus 0.34 and the third one is plus 0.4. So this is a direct form 1 structure. I will minimize it so that we can draw direct form 2 also side by side. In direct form 2, this storage element Z inverse that is combined together and first pole is realized. After that zeros are realized. So first we'll realize the pole part. So there will be 3 delay element. In the first pole part, the first coefficient is minus 0.6. The second coefficient is minus 0.34 and the third coefficient is 0.4. Sorry, here two, one summation. And in the zeros part, first coefficient is 0.56. The second coefficient is 0.638 and all are summed together and third coefficient is 0.08. Okay, so this is the direct form 2 and this is the direct form 1 structure of the given transfer function. So now we will take one more example, that is the cascade realization. Okay, obtain cascade realization of the system characterized by the transfer function h of z, that is equal to 2 into z plus 2 divided by z into z minus 0.1, z plus 0.5, z plus 0.4. So here now what we'll do, we will do some manipulation. So multiplying both the numerator and denominator by z to the power of minus 4. Okay, multiplying numerator and denominator by z to the power of minus 4. What we will get? We will get h of z, that is equal to 2z to the power of minus q 1 plus 2z inverse divided by 1 minus 0.1 z inverse. We are dividing all by z. Okay, so that is z to the power of minus 4 and here z to the power 4. Okay, or you can do here z divided by z to the power of q. In this way we can do. So after that we will get 1 plus 0.5 z inverse 1 plus 0.4 z inverse. So that is equal to 2 into z to the power of minus cube dot 1 plus 2 z inverse divided by 1 minus 0.1 z inverse dot 1 by 1 plus 0.5 z inverse dot 1 by 1 plus 0.4 z inverse. So this is just the cascade form, like the transfer function hz can be written as 2 into h1 of z into h2 of z into h3 of z into h4 of z. So this is just the cascade form. This one is h1 of z, this is h2 of z, this is h3 of z, and this is h4 of z. So now the realization structure will be like this. First we will give xn. This will be 2. After that h1 of z is 3 times z inverse. So this is our h1 of z. Now 1 plus 2 z inverse and the coefficient is 0.1 in the pole and 2 in the 0. So we will use direct form 2 so that we will require less storage element. That's why pole is taken first and then zeros. So this is our h2 of z. There is no pole, no zeros, so we will take the pole part, that is minus of 0.5. So this is our h3 of z. Similarly, we will take h4 of z. This will be minus 0.4 as a coefficient, and this is our h4 of z. And now here we will get y of n. So in this way we can obtain the cascade realization of the system. So today we'll end up the lecture here only. If you have any doubt, you can see this lecture. This video will be uploaded on YouTube. Link will be shared in the NPTEL portal. If you have any doubt, you can ask in the comment section of the YouTube. Thank you so much. This is the last lecture, and all the best for your test. And thank you so much for choosing this course. Thank you so much.